Hello and welcome to Automating IP and SoC Verification, presented by Agnisys. I'm Tom Anderson. There are many challenges associated with the hardware RTL development of modern semiconductor devices. For a start, there's the sheer complexity. Modern chips may have billions of gates, thousands of blocks, and hundreds of thousands of interconnections among those blocks. The size and complexity means that you really can never write such a chip from scratch. You can't sit down with a blank editor and develop all the RTL. You need to reuse as much as you can from other sources. That reuse might come from internal IP teams or external IP providers. It might involve sharing designs with other teams in your company or perhaps reusing portions of previous designs. And much of that reuse involves standards or portions of the design that are used in multiple types of chips. But no matter how much reuse you can accomplish, you're always going to be writing some RTL from scratch for the novel parts of this new chip. That's manual coding, and any time that you have manual coding, you have a chance of introduced errors. Of course, people do make mistakes, and you consume time and resources on a project. Now, if we think about the development of a system on chip or SoC device, there are additional challenges that come into play. For one thing, there are more teams involved. You have the development of the algorithms and the high-level approach by the architects and the implementation in RTL by the hardware design team. You have the hardware verification team that has to make sure that the RTL works as expected. You have the firmware team who develops the low-level driver software that talks directly to the hardware, and then the product validation team. Just simply plugging together all the blocks at the top level is a challenge all by itself. It sounds easy, but it's a big project. The IP blocks must all be connected properly and verified to be connected properly, and only then can the system validation phase proceed. That involves compiling the C++ programs into the embedded CPU models and simulation and verifying the hardware and software portions of the design together. Now, there are also challenges related to the specifications for these SoCs. For a start, there's no standard way to capture a specification. People generally use natural language, but natural language, although it's understood by everyone, is inherently ambiguous and may very well be interpreted different ways by different teams. In fact, many chip bugs are due to exactly that problem. Different teams, the hardware and software teams, or two different hardware teams, interpreting a portion of the specification differently, and therefore everything does not work together properly. That's not just a problem at the start of the project, that's a problem throughout the project because specifications change many times over the course of the project. There may be implementation issues discovered that have effects that require specification changes. There may be new competitor offerings with new features that you'll want to add to your specification and to your chip. Many reasons why specifications change, and every time they do change, you get this waterfall effect where, well, maybe the hardware has to change. Well, okay, then it has to be re-verified. Well, maybe the software has to change too, and then the hardware and software have to be validated together, and almost every time you have to change the documentation. And so if all these changes are manual changes, you're introducing risk, you're greatly extending the life of the project, length of the project, and the amount of resources required, and that's just not a good thing. There is only one solution to this, and that is automating as much of the SoC development flow as we possibly can. And it turns out, fortunately, that many portions of the chip can actually be specified in a way that is unambiguous, and it's actually executable. And by executable, we mean that you can actually generate models and code and documentation directly from those specifications automatically. That's a great boon in terms of saving time and effort on the project. Let's look at a few examples. Let's say you have an executable specification for the registers and the memories in your design. From that, you can push a button and generate the RTL code that implements those registers and memories, the UVM test bench models and sequences to verify those memories, the C and C++ driver code to program and access those registers and memories, and the associated documentation. If you have custom sequences in your design for the novel portions of the design, these non-standard portions, then you can define those in a way that you can generate the test bench sequences, the corresponding sequences in the C++ driver code, and again, documentation. For the standard portions of the design, you can have a library of standard IP blocks that again automatically generate all these different models that we've been discussing. And finally, for interconnection at the top level of the SoC, you can have a hookup specification that automatically generates the RTL design code for the top level of the SoC as well as associated documentation. Now, who benefits from this automated flow? Everyone on the project. Every project team benefits from this approach. The RTL design code, of course, goes to the RTL designers. In addition to the portions of the chip they're hand coding, they now have big portions of the chip that are being automatically generated for them. Of course, the verification engineers are taking all this RTL code and verifying it, making sure that it matches the specification. They also receive the test bench models and the programming sequences for running in simulation. The driver code, C++ code, goes to the verification team for the validation portion of their efforts. So when they actually are downloading this code and running it in embedded simulation models of the embedded processors, then they're doing a hardware-software validation effort. But the C++ driver code also goes to the embedded programmers who are using it as building blocks for their firmware and their other types of low-level programming code, and being run in the lab by the bring-up team. Once the chip is fabricated and back from the foundry, you can actually run the code and physical chip as part of the bring-up process. And finally, the documentation, of course, is transformed into customer documentation by the technical writing team, but it's also used during the project by all the project team members to make sure there's a consistent view of the design. How do Agnisys products map onto this flow? Well, for the register memory specification portion, we have iDesign Spec IDS and Automatic Register Verification, ARV. That performs the design and verification portions of this flow for registers and memories. For the custom sequences, that's provided by iSequence Spec, ISS. The top-level SoC verification test bench is provided by Specta AV. SlipG is the Agnisys library of standard IP blocks, again, generating all the appropriate models and documentation. And finally, SoC Enterprise supports a chip hookup specification that allows the generation of the top-level RTL for the chip and the end-user documentation. There are two additional products that sort of overlay this flow. IDS NextGen, or IDS NG, is a common front end for the entire flow and for all the different tools. And DV Insight is a checker and editor for System Verilog and UVM code. Let me tell you a little bit about Agnisys as a company. Agnisys is the EDA SoC development automation leader. The company was formed in 2007, starting with the register automation portion and now expanding into all the other things we showed you on the previous slide. The company is privately held and profitable. It is headquartered in Boston, but it has design centers and support centers around the world for efficient and timely support of their customers. And in fact, Agnisys is well known as a company who's good to work with and who provides aggressive and industry-leading customer support with about 1,000 users worldwide, hands-on users, about 50 customer companies, and a response time to user inquiries within a matter of hours. So to summarize, SoC development is incredibly complex. That's clear to anyone who works on an SoC project, but sometimes when you're sitting trying to solve your own problems, it's hard to appreciate all the other teams and the issues they're facing, how the interactions among your teams can compromise the final chip if you don't have a consistent, automatic, executable flow for as much of the chip design as you possibly can. Again, spec changes are a major portion of this problem. It's not just a one-time problem. As you do the initial coding of the design, every time the spec changes, the ripple effects and the waterfall effect cause additional problems. So the only answer is to automate the hardware design, software coding, verification, validation, and documentation. And that's what Agnisys does. Agnisys solutions save valuable time and project resources, not just once, not just during the initial coding, but every time the specification changes over the course of the project. So thank you for listening, and I encourage you to learn more about Agnisys and its products.